Hey guys, just doing a short follow-up video for this week. Wanted to talk a little bit about breaking down some of the more ambiguous concepts. So I'm going to start out by talking about Vmax. So Vmax is actually a hypothetical number. So we have some sort of a rate and some concentration of substrate here. When you add in substrate to your enzyme, you initially have this linear phase and then it tapers off, something like this. And then we have what's termed as Vmax, or the maximum velocity of the enzyme. So you may know that I'm not making this line here. Well, I missed it a little bit. Here, where I'm actually hitting the top, what I'm making is a line that is above the rate that we're actually observing. Vmax is the hypothetical maximum. Enzymes never actually reach it, because when you hit a certain substrate level, you actually start getting substrate level inhibition, and your rate starts to go back down. The only way to actually calculate a Vmax is through using a Lineweaver-Burk plot, which I'll talk about in a second. But just so you know that when you're calculating these, and you guys have one in your lab for this week, it's not just going to be this maximum point here. You have to actually use the Lineweaver-Burk to calculate your little dotted line shown over here. So what this Lineweaver-Burk is, or you could go back to this image here and plot whatever 1/2 Vmax is. And figure out your substrate concentration for your Vmax that way. Is an extrapolation where you do a double reciprocal. So you have 1 over rate on your y-axis and 1 over substrate on your x-axis. And by doing this and plotting these points, you're able to extrapolate using a line what the Vmax actually would be. So your y-intercept here is going to give you 1 over the Vmax, and this is the only way to actually calculate that. From there, you can either use the x-axis to get your Km. Okay, the other concept I wanted to talk a little bit about was rate constants. So rate constant is probably something that you guys have not seen in a long time. You learn it in general chemistry. So rate constant is something like, for a first order reaction, we have a rate constant or a rate that looks like this here. And I'm actually going to use A instead of S. For a second order, you'll have a rate where instead of just having one thing that affects it, like you do up here, you're going to end up having 2 different functions which affect it. Whoops. So it's going to rely on both the rate of A, or the concentration of A, and the concentration of B in order to determine. Third order, also what you'd expect. Now you have 3 things that are going to affect it. So you'd have A, which is really hard to see. B, and if I can draw in there, C. Okay, so how does this affect our Michaelis-Menten equation? So if you take a look at this Michaelis-Menten equation, I'm going to redraw it a little bit. So Vmax is equal to kcat times total enzyme concentration. And that gives us a Michaelis-Menten equation which is very complicated. So you have a lot of different components here. It doesn't really behave any of these first order, second order, or third order equations because you have two different constants, one on top, one on bottom, and then these three different substrate concentrations here. What happens though is that at high enough substrate concentrations, so I'm just going to redraw this. These rate orders that we drew earlier, first order, second order, and third order, it's fairly obvious that we're mimicking, I'll do it in blue, this second or first order equation that is shown here. Next page. Yeah. At high enough substrate concentrations, where the substrate is much greater, draw on the side, than Km, Km is no longer relevant. So if you think about it, if substrate concentration was 10,000 and Km is 1, the difference between having Km there and not having Km there is, oops, one too many zeros, less than a percentage point, less than 0.1% difference between those two numbers, so it's essentially negligible. So at that point, you can cross out Km here, and now we're just left with the equation shown here. And if at this point in time we cross out our substrates, we're left with a rate equaling some concentration plus a or kcat times our total enzyme concentration. So if we take this and we look at, so I'm going to draw that or rewrite that what a first order looks like next to it. Or it should be A. So when they say that at high substrate concentrations, your Michaelis-Menten behaves as like a first order or a pseudo first order reaction, this is what they're referring to. I hope this helps you guys a little bit with this chapter, and I will talk to you guys again next week. Thanks.